Today we'll learn how to do sensitivity analysis for the predator-prey system. As you know, there are several examples of the predator-prey system. What you see at the bottom right is the typical population behavior of both the predator and prey as a function of time. You can see that both the populations oscillate and in this video our goal is to find out how these oscillations vary as a function of the different parameters of the system. So here is a simple mathematical model of the predator-prey system. You can find more details about the assumption used in this model in the Wikipedia article, the link of which is shown below. Okay, so the rate of change of the prey is proportional to its birth rate minus the death rate. Here alpha and beta are the rates at which the prey population is growing and the prey population is dying because of the interaction between the predator and prey. Similarly, the rate of change of the predator depends on some birth rate for the predator and how much prey is available for the predator to feed on. Similarly, there is some first order death rate for the predator. So in addition to the equations, we need the initial conditions to solve this system of equations. Let's say we know the predator and prey concentration at time 0. Okay, if we solve these equations, we get different results depending upon the choice of the parameters used. Both the frequency of the oscillations varies, the maximum and minimum to which the predator and prey's population size goes to vary. So several things can vary depending upon the initial conditions and the parameters used. So in this video, as I said, we'll focus on how the time period of oscillations varies as a function of the parameters and the initial conditions. Okay, so we'll talk about the local sensitivity analysis method first. So using this method, we can answer questions like how does the time period vary if, let's say, we use let's say the predator and prey in this case are cow and grass. Let's say we use a different types of grass which grows twice as fast as another type of grass. We want to know how the time period of oscillations change. We can also answer questions like, let's say the cows die faster due to some disease. We can identify how the oscillations change using this method. Okay, so in this method, so we change one parameter at a time and find the output, the change in the output, and we calculate the local sensitivity and index, which is given by this formula: the change in output divided by the output, and the change in the parameter divided by the parameter value used. So for example, let's say these are the values of the initial concentrations and alpha, beta, delta and gamma with which we start. And let's say we increase the value of alpha by 50%. This is the old time period with the old values, and we increase the value of alpha by from 3 to 4.5 and keep all other parameters as previous. So there is a new time period which is smaller than the other time period. So we can calculate the sensitivity index. Here the output is the time period. So we calculate the change in the time period divided by the previous time period. In the same way, we divide it, we calculate the change in the parameter values from 4.5 minus 3 divided by the nominal value used for the parameter. So that way we can calculate the sensitivity index. We can do this for every parameter. So as you can guess, the name local sensitivity, from the name local sensitivity analysis, we can change only one parameter at a time. If we do that for all parameters by changing one at a time. So here I have a plot of the local sensitivity and index as a function of the different parameters of the model, where I changed it by either 10% or 50%. Both cases I increased. So all values below the horizontal line show that the change is negative. All values above show that an increase in the parameter leads to an increase in the output. So by plotting results like this, we can tell that the output, in this case the time period, is insensitive to changes in the predator or beta values, but it changes with changes in the value of alpha, delta, gamma, or the change in the initial condition for the prey population. Also you can see that the local sensitivity index value changes whether we use a 10% increase or a 50% increase. It's more clear for the value of gamma here. So such an analysis will help us identify how the changes in the parameters are affecting the time period. Okay, so the advantage of this local sensitivity analysis method is it's computationally inexpensive. However, the limitation is we can only change one parameter at a time and see the effect of the change in that parameter on the output. Okay, so the other method we'll talk about is the global sensitivity analysis method. So again, even though we talk about fixed value of the parameter, in reality the parameter values are changing over a range. For example, the birth rate need not be 3. It can vary from in this case 1 to 15, depending upon the choice of the grass we use, or within the same grass it can grow. We might not be able to pin down a fixed value for the growth. So in the same way, for every other parameter there are ranges. So with global sensitivity analysis we can answer questions like, if we know that if there is an uncertainty in all these parameters, how much is the output influenced by this change by a particular parameter given this uncertainty. And that helps us to identify which parameters should be more accurately measured so that we can reduce the uncertainty in the output value. Okay, for this there are several methods. We'll talk about a method using latent hypercube sampling and then calculating the rank correlation coefficients. We'll not go into details of the mathematics behind it. We'll just use we'll just learn how to use this method to answer the questions. Okay, so we'll use MATLAB for this purpose. For latent hypercube sampling, we'll use these keywords from MATLAB called LHS design or LHS norm. So what we do in this method is we'll split the range of the parameters into a certain number of intervals. Let's say for the prey initial value we have a range from 11 to 100. We'll split it into 10 intervals from 11 to 20, 9 intervals from 11 to 20, 21 to 30, 31 to 40, so on. So in this we'll do the same thing for every parameter. Once we split into the range, we'll pick a value from the range with either same probability, in which case we are using a uniform distribution to pick a value from each range, or we use a normal distribution where the central values are have higher probability of being picked. So we do that picking for every parameter. Let's say the prey concentration initial value, we pick this value. The same for predator initial concentration, we pick a value somewhere in the range, and we do that for every other parameter. Once we have a value picked for all the parameters, we run the simulation, and we do this running simulation several times by picking different values randomly within the ranges for the parameters. Once we run the simulation several times, we can calculate what's called a PRCC value. With MATLAB, the keyword you can use is partial core to identify the PRCC value. PRCC stands for partial rank correlation coefficient. These can be used as sensitivity indexes. These values vary between -1 to 1, and these values I've plotted here on the y-axis. On the x-axis are the different parameters, and these values change with the number of runs. You get higher and higher accuracy as you increase the number of runs. But you'll see that after a while the values more or less stabilize. So that's the runs you should choose for to identify the correct PRCC value. Okay, so from this plot you can see that the output, which is the time period of oscillations, is most sensitive to the value of alpha and gamma. These results are different from what we obtained before with the local sensitivity analysis, because with local sensitivity analysis the answer depends on where you start from and how much you increase. But in global sensitivity analysis, the answer depends on how much is the range over which the parameter is varying. And again, the answer will change depending, for the global sensitivity analysis, will change depending upon the number of intervals you choose, the number of runs you choose, and you need to optimize it so that you get the correct result. Okay, so the advantage of this method is you don't have to fix a nominal value. You can use the entire range over which the parameter is changing. And on the limitation side, you must have guessed that it will be computationally expensive, and it will change with how expensive it is depending upon the number of parameters you use and the number of runs used for every simulation. And another big limitation is this works only for a monotonic relation between the parameter being studied and the output. For example, this method works only if the time period increases or decreases with the parameters. It cannot happen that the time period increases for a certain range of the parameter and decreases for another range of parameter. This method cannot work in that case. So we have to make sure that the relationship between the property of measuring and the parameter is monotonic. So in both the methods we discussed, the output chosen was the time period, which was not changing with time. However, if the output is changing with time, you can still do the local and global sensitivity analysis, but in that case you'll have to find the sensitivity values at every time point. So then you get a plot. You can plot the sensitivity as a function of time for every parameter. And I said that the limitation of the global sensitivity analysis, is it doesn't work for a non-monotonic relation between the output and the parameter. So in such cases, you can use advanced methods like the variance-based methods. For example, Sobo's method and E-fast method, which is based on the Fourier amplitude values to calculate the sensitivity indexes.